Uh, Hello, good afternoon, everyone. Can you hear me?
Can hear you, sir.
Okay,
Afternoon,
thank
sir.
you. All right. Right. Today we're going to talk about, discuss a little bit about our learning unit number 6, which is very much on the bandwidth utilizations and which is specifically focused on multiplexing and spreading. Okay, let me share my slides. All right. Yep. As you can see, let me see. Okay. Show chat. All right. So this one, let's talk about the general usage of the bandwidth itself. So what is bandwidth here? We are talking about bandwidth is actually how much data you can send over a transmission channel. And then how much data you can send is actually, there are a lot of factors. For example, as we have gone through our physical layer on the transmission media, you can see that different transmission media will actually give you different type of bandwidth at the physical layers. And then, this transmission media is actually carrying the signal. And then what kind of frequency this signal can actually carry will decide how much bandwidth you're going to get. And I mean, in simple term, for the computer system, for the computer sending digital data, most of the time we talk about bit per second. So those are actually sending, the bandwidth for sending digital data. But before we go into that, we'll have to talk about the bandwidth in terms of the signal itself. Because as you all remember, our 1 and 0 has to be carried by some analog signal, isn't it? So these analog signals come in a waveform. And then each of these waveform come with a frequency. And each of these frequency will actually decide how much bandwidth you can actually, carry by that particular signal. And then what kind of frequency can you run on a transmission media is also limited by the transmission media itself. So not all the transmission media are good to transmit at high frequency. And of course, as you can transfer at high frequency, then you will get a higher bandwidth. Now, this is actually by analogy, by the perspective of the higher frequency your transmission media can carry, then the higher the frequency, then the higher the bandwidth that is available. Right? So when this frequency is carrying your 1 and 0, then your bandwidth is actually measured in bit per second. Okay? And then if it is not carrying any 1 and 0, or what we call digital data, then it is actually the bandwidth is measured in hertz. Okay? It's actually based on the frequency. Hertz, how many hertz? The larger the hertz, actually the larger the bandwidth itself. And then all these things happen at the physical layer. So you have to understand this, we're talking about this bandwidth here. The most fundamental is all happening at the physical layer. And then you still remember in our last learning unit, we talk about we talk about modulation. Modulation is another technique that can actually, push the limit of your transmission media so that it will carry a higher bandwidth by squeezing, I would say, by squeezing some of these periods of the bit itself, so that you can squeeze more bit. For example, if you have a transmission media that can actually deliver 1 megabit per second, then if you apply a higher order modulation scheme, then you will probably get 2 megabit per second, or even you get 4 megabit per second, you see. Right, so those are actually the additional technique riding on top of what the transmission media can actually offer. So those are actually what we call the additional the modulation technique that we can apply, we can add on, try to squeeze more bit into the transmission channel. So this concept, I hope this can be clear. Otherwise, you're gonna get confused about this. So bandwidth initially is all about analog signal, traveling along a transmission media. Some of the transmission media can only deliver low frequency. For example, like the coaxial cable. Coaxial cable probably can only deliver up to 16 megahertz only. So with 16 megahertz, you cannot have too much of bandwidth available because your frequency is limited to 16 megahertz. So probably you can only run at 10 megabits. If you actually carrying digital data, you will probably get just maybe 10 megabits only. You cannot go to 100 megabits because the frequency that you are carrying is too low, and that kind of transmission media cannot carry high frequency. So when it carry high frequency, you will experience a lot of losses. So that is really very much depending on the transmission media itself. That's why we are actually changing to use twisted pair. Okay, a high quality twisted pair cable will have a higher quality cable. Not only that, but it will have more twists per feet. So if you look at the different category of twisted pair, we have category 3, category 5. Okay, now the one that is commonly used for us to support our gigabit network is actually category 5E or category 6. So if you look at those, as the category increase higher, then you will see the thickness of the cable is getting thicker at the end, and then at the same time, the number of twists per feet, is actually getting higher. So because of that, that kind of cable can actually carry higher frequency. So when they can carry higher frequency, then indirectly, I would say directly, they will be able to offer higher bandwidth. So those are actually the logic behind this. So if you check the specification of all those twisted pair cable, different category, they will having different supported frequency. For example, category 5 probably will support only 100 megahertz. So you have category 5E. Category 5E probably you can support like 250 megahertz. So you have category 6. Category 6 probably 300 megahertz. So on and so forth. So when you have category 6A, so probably you will go up to 500 or 600 megahertz. Because by being able to carry higher frequency type of signal along the cable, then the bandwidth for that channel, for that cable can offer is actually relatively increased as well. So if you want to run gigabits, so you at least have 250 megahertz running on your transmission media itself. So this is actually talking about the bandwidth. So we have bandwidth, and as we all know, we have a lot of user in our network. So a lot of user in our network, we would like to share, we would like to optimize the use of the cable so that we don't want to waste the number of cable. Everyone, if you still remember the mesh topology, right? The mesh topology, everyone will have to establish a physical connection to all the other machine in the network, which is not efficient at all. See? So we need to share. So now in the physical layer, so there's this technique that we can share. We can pack, we can squeeze a lot of people's different users' data together under the same transmission media. And then this is actually the technique, what we call multiplexing. And this multiplexing has been widely used. And remember, this multiplexing technique is actually happening in the physical layer. So this is not at a higher layer. This is always at the physical layer, meaning to say that it happened at the signaling level. Right? Physical layer. Right? So, okay, here. Right. So the multiplexing techniques is actually allow us to make efficient use of our bandwidth that is available, so that you can share. You want to share, you have to use multiplexing technique. So these multiplexing techniques allow multiple people to share the same transmission media, so that they can actually, everyone can deliver their data at the same time. So that is what we call multiplexing. If you're only one user is actually using that transmission media, sometimes it can be a waste because that user cannot fully utilize because that user just do not have that much of data to send. And then because of that, that give a lot of space to share with other people. But okay, this is just like carpooling, you see. So when people say, oh, carpool, we want to reduce the number of vehicles, on the road. So we have to do carpooling. Also carpooling because if you are only one person inside the car, you got how many empty seat? You already got another 3 more empty seats. So you can, carry other people, you see. So it's the same thing. Multiplexing technique is, you can imagine them just like carpooling. One car shared by multiple users, you're all going towards the same destination. And there's another technique, what we call spreading. Spreading is another technique that usually used in a wireless transmission. And then this spreading, as the name implies, you will spread the signal basically. When you was trying to spread the signal. So as we all know, wireless transmission is actually not so secure because wireless, right? Everyone can pick up the signal. So there is no boundary to actually restrict the signal so that it is not being picked up by anyone. So, as the moment when you broadcast in wireless, a lot of people can actually receive it. So how do you ensure privacy, right? How do you ensure privacy in your wireless transmission? So you can use this technique called spreading. And also at the same time, when you are actually openly broadcast your wireless transmission in an open space, your enemy, for example, someone want to sabotage your wireless network, they can always introduce a jamming signal. They can always jam your wireless transmission by introducing another jamming signal. For example, while you are talking, right? What do I mean by jamming is, while I'm talking to my class here, then suddenly there is someone outside the class here, and they try to shout very loud or play very loud music. So those music very loud is going to disturb my communication with my student. So my student cannot hear me, you see. So those guys who play loud music outside the class is actually try to jam my channel. See. So those are what we call jamming. See. So you can introduce different type of frequency to jam a transmission of a network. And this thing happen a lot. See. Right. So spreading is also one of the techniques that allow you to do anti-jamming. Okay, so that people cannot jam your signal, so that even though you are in a very noisy environment, so you can still have communications established successfully. Right. So today we're going to talk about these two things. Okay, I'm going to talk about the important parts of it. Right. So when in terms of multiplexing, we have basically 3 types of multiplexing. In general, we have three types. We have frequency division multiplexing, wavelength division, and then we also have time division multiplexing. So you just look at the name. I want you to look at the name carefully. Frequency division, you divide what? You divide the frequency. Okay? Wavelength division, you divide what? You divide the wavelength. That means you divide the wavelength, and then when you talk about time division, you divide the time. Right? So you have to, based on the name, then you roughly know how does each of these multiplexing technique works. Okay, so if you look at this diagram here is when you do not have multiplexing, so each of the user, let me see if I can go back to. Oh, okay. Okay, when you do not have anything, then you just have to have a dedicated connection to each of the user. So this is without multiplexing. So you are going to have 1 link, 2 link, 3, and 4 link here, all together. So it is going to be it's actually waste of resources, waste of transmission media. So with multiplexing, so you actually employ a multiplexer and the multiplexer over the other end. So you're just running on a single link. So 4 users, 1 single link. So everyone happy. Right. So this is actually another diagram to illustrate the concept of multiplexing. So basically combining the a multiple user onto the same link, same physical link. But within that, each of these physical link, you may have multiple channels. You got each channel for 1 user. So basically, you are multiplexing multiple channel. and multiplexing multiple channels into the signaling. Right, so these are actually the three different types. So let's look at frequency division multiplexing. Frequency division, you divide the frequency. In fact, if you look at this diagram here, so the amount of frequency allocated is actually this much. And then this frequency, let's say, is actually, let's see, let me put it this way, easy, 9 megahertz. The total bandwidth is actually 9 megahertz, let's say. So you divide this into 3 different channels. So each of the channel will actually get 3 megahertz. So you divide, just like you have a piece of cake. So you want to divide among 3 people. So you just slice them into 3 pieces. Each of them will take their own piece. So they will not interfere. They will not interfere each other's. Of course, you cannot have the whole cake now because you have to share with 3 different people. So the whole concept of frequency division multiplexing is actually you just slice them physically. Okay, each of them take 3. Okay, you have 3, 3, 3. 3, 3, 3, you get 9. So total is 9. So each of the user will get 3 megahertz instead of get 9 megahertz. So if you, let's say, the whole system, the whole channel here, okay, the whole physical link is only for 1 user. So that particular user will get altogether 9 megahertz of bandwidth. But now, because of we are using, frequency division multiplexing, and then share by 3 users, so it's actually going to be 3, 3, 3. And then based on the belief that each of the user will not need more than 3 megahertz of bandwidth in this case. So if each of the user only need, like say, 2 point something megahertz or even 1 megahertz, so the way you divide the frequency like this, then that will be just nice, right? So this is one way of sharing, and this type of technique is what we call frequency division multiplexing. And then if you look at this diagram here, it is even easier for you to actually understand. So if you look at this one, this whole piece is 540 kilohertz of bandwidth for that particular physical link, for that particular link. So it's 540. So it's being divided into 1, 2, 3, 4, 5. So it's actually 5 different channels. So each of the channel will actually take 100 kilohertz, 100, 100, and so on. So it's altogether 5. So, but your total bandwidth is going to have 540. So remember, you will still have to have a guard band, because normally people use frequency division multiplexing. They have to put a guard band. It's something like what we call pagar. It's something like a partition, so that the frequency will not overflow to each other. What do I mean by frequency overflow? Let me draw the diagram. Frequency overflow is something like this. Supposingly, your signal is like this. Okay, this one is ideal. Exactly what you have here. But overlapping means what? Overlapping means when you actually signal too close to each other. You see the overlapping part? These are the overlapping part. So when the signal overlap, so they will actually having distortion with each other. So this is what we don't want to see. Okay, these are the distortion because they overlap here, right? Because they overlap, that's why we don't want to see that kind of thing from happening. That's why we put guard band here. So we put a guard band here to actually make sure those signals do not overlap each other. So those are actually 5 different signals running inside the same cable, 5 different frequency running into the same cable, and then each of them being separated by a 10 kilohertz guard band. In this case, it is being separated by 10 kilohertz guard band to make sure that they do not overlap. So those guard band is what we call the partition, or what we call the pagar. You want to jaga, you want to take care of your signal so that they won't overlap. So that is a characteristic of the frequency division multiplexing. Most of the time, imagine you are using a FM radio. You still remember you listen to your FM radio station, your FM radio, your favorite DJ and all those things. So every time when you need to tune to a right frequency number, to tune into that particular channel, isn't it? To tune into that particular radio station. So this is exactly the same thing, because for FM radio, they are using frequency division multiplexing as well. Exactly the same one. But that one is on a wireless channel. That's why in a wireless channel, that was even more important to introduce a guard band, right? So this one could be, the first one could be FM1, okay, FM1. The second one could be FM2, okay. So they all run on different frequency. Remember the frequency that you are tuning, something like 88.9, 90.6. Okay, so those are actually the frequency for that particular channel. So one frequency is actually one user, one channel. So you can start to imagine that when you actually tune into your FM radio, you always have, when you change your channel, when you change your station, you are switching around from one frequency to another frequency, which represent a different radio station. Okay, so this is exactly a live example that will actually help you to understand better on the concept of FDM. Okay, so as we all know, for all the multiplexing technique, they always come with a multiplexing and a demultiplexing process. So it's actually something like a compressed then an uncompressed process, right? So this is always the case. You multiplex it, then at the end of the transmission, you have to demultiplex it so that each of the user will actually get what they have. And then the process of doing multiplexing is called the multiplexer. The device that will perform multiplexing is called the multiplexer. And then the device that is actually performing the demultiplexing process is actually called the demultiplexer. So you should see these two devices at the end of the share link. Right, so this is another example. I mean, a lot of you are having experience with, streamings at home. Last time, streamings running on telephone cable, or what we call the TM streamings. It's basically an ADSL application. So you can see that if you look at this graph here, so 0 to 4 is actually dedicated for voice, and then this is for data. You can see this one is used for data. Then you have upstream and downstream. What is upstream and downstream? Downstream is download. Upstream is upload. Right. So you can see the downstream is actually much faster as compared to the upstream. Why? Because TM believe that most of the user will actually do more downloads as compared to them do uploads. That's why they allocate more bandwidth for the downstream and then less bandwidth for the upstream. And you can see that how much bandwidth is this one. See? 138 until 1104. Okay? So this is actually how they do frequency division, multiplexings on your telephone line. So your telephone line basically carrying three different signals. One is for voice. When you are using ADSL, this is actually the technology that is being used for what we call the streaming services. Not the Unify. Unify is different. Unify is using fiber optics. This one using telephone cable. So your telephone cable is basically carrying three different set of signal, and then they all run at different frequency. If you check the frequency, this one is 0 to 4 kilohertz. The second one is 26 to 108. And the third one is 138 to 1104. Right? So they're all operating at different frequencies so that they won't interfere with each other. So in between of them, is there anything in between of them? Yes. There's actually a lot of empty space in between of them to make sure that those frequencies do not overlap. Right? So when they do not overlap, they do not interfere each other. So this is actually very important for frequency division multiplexing, where each of the channel shouldn't be overlapping with another channel. The moment when they start to overlap, then your signal will experience distortion and your data will be corrupted. Okay? So this is exactly what we do not want to see when we apply frequency division multiplexing. Right? So I hope you get the idea. This is another example. And then the application of FDM is actually widely used in telephone networks. So this is exactly what you see in a telephonic hierarchy system. Okay? So all these will be combined, where this is actually the telephone at your home and your neighbor's home. They will combine under one group here. And then you have multiple group here, combine again. Then you create a super group. Then many super group combine again, create a master group. So many master group combine again, create a jumbo group. Okay, so this is actually from your housing area to regional, to state-wise, to countrywide, and then to, maybe this one is going all the way to the international. I'm going into the international. So this is exactly what happened to our analog telephone system. Okay? And another one, the moment when fiber optic coming into the picture. So this multiplexing technique is actually very specific to fiber optics. And because wavelength is actually refer to a very high frequency. That's why they don't use frequency, they use wavelength to indicate each of the signal. In fact, F equal to 1 over lambda, right? This lambda here, if you look at this formula here, this lambda here is actually your wavelength. And this is your frequency. Okay? Frequency and wavelength. So basically, wavelength and frequency is the same thing, but just to differentiate them, because on the fiber optics, they are using lights. And then lights, we all know that lights are actually running a very high, extremely high frequency. So when lights are on a very extremely high frequency, so they would like to use wavelength. Meaning to say that if your fiber optics can allow multiple wavelength to enter, this means you can allow multiple lights to enter your fiber optics. So one single fiber optic can be shared by multiple users by allowing multiple light source to actually shine into the fiber optic itself. So each of the light source is actually represented by a wavelength, right? So that is the whole idea. It's the same thing. So if you look at this diagram here, each of the light source here, they're all having their own wavelength. So this is wavelength number 1, wavelength number 2, wavelength number 3. So these wavelengths are actually all different wavelength, just like different frequency. So when actually, being multiplexed by wavelength division multiplexer, so this is what happened. All the 3 wavelength is going to be traveling inside the same fiber optics. And towards the end, there's a demultiplexer. Okay. This is MUX, this is DEX. Then demultiplexer. So you can actually get all the signal again. Right, so this is exactly what happened to the wavelength division multiplexing. And then this one is only happening to fiber optics only. When your transmission source is not a signal, but it's a light. Okay? This is exactly what we're talking about. Right, let's talk about the time division multiplexing. The time division, as we all know, this is one of the most popular. This is one of the most popular multiplexing techniques that's being used. Why? Of course, they have their own advantage. Time division, you divide the time. You imagine if you can slow down the time, okay, just like when you watch some movie, this guy Flash can run so fast that it can slow down the time. You see, so the moment you can slow down the time, you can do a lot of things. So time division multiplexing is just like you're dividing the time. So if you can divide the time into smaller slices, then you can do a lot more things. For example, 1 second. If actually 1 second shared by 10 people, each of the user will actually get 0.1 second, isn't it? So 0.1 second, is it a lot? Maybe to us, 0.1 second is so little only. So what can we do in 0.1 second? Maybe you don't appreciate this, but in a computerized system, when we have a time, 1 second, so we divide them into, let's say, 10. So each one will actually getting 0.1. So what does this 0.1 second means? So each of the user has got 0.1 second, meaning to say that this user has got 0.1 second to actually use the channel, to use the entire cable, 0.1 second. As long as within that 0.1 second, the whole channel is yours. After the time finish, then the second user will use it. Just imagine this one is, I always like to use toilet. Sorry to say, when you share a toilet, when you use the toilet, the whole toilet is yours. So no one is going to squeeze in and then share with you at the same time. No. But frequency division is meaning to say that multiple users share the toilet at the same time. Okay. So that is actually frequency division multiplexing. But for time division multiplexing, as you know, that it's about the time of using. So everyone share. When it is your turn, then you go in and use it. When it's time's up, you have to get out. So the second user will go in. And then they start timing 0.1 second. Once time's up, you must get out. The third user get in. So it's just like we share classroom. We have one classroom we can share by throughout the day. Yeah, we can share by multiple classes, use for multiple lectures. 8 to 9 o'clock, one class. 9 to 10, another class. Right? So you are still using the same classroom. So this is how we optimize it. Okay, so this is the concept of time division multiplexing. The whole good idea is that this time here to a computer, to a CPU running at gigahertz, if you look at a CPU running at gigahertz, so it is actually very, very fast. So when this CPU running so fast, 0.1 second to them is a lot of time, you know. So they can do a lot of things inside such a short period of time. The moment when you increase the CPU clock speed, then you can slice the time into even smaller. For example, you can slide this into maybe 0.0001 second. Okay, you can even slow it in 0.0001, maybe 0.0001 second. Okay, so because we can slide the time so small, then you can support a lot more user. See, you can support a lot more user. So the cable itself can be shared by a lot more user because of your clock can run so fast. As a user, you cannot, but as a computer system, you can, you see, because computer system running by the clock speed. So the performance of a TDM system can actually improve by improving the clock speed of your CPU. So you can increase the clock speed of your CPU, which is for the transmitter itself, the clock speed of the CPU for the transmitter, then you can actually increase the performance of the TDM so much. So without the need to do anything. You just need to increase the CPU speed, then you can support more users. Right. So this is actually the general concept. Imagine every time it's only 4 users. Okay, 4 users. So this is first round. This guy send first, then followed by this guy, followed by this guy, and then repeat again. See? It will repeat again. And then it will repeat again. Okay? This is just like taking turn. Imagine you go to a restaurant. So there's only one table. So 10 people, four people want to share that table. So you will share by the time. So everyone is given 1 minute to eat their meal. After you eat for 1 minute, then you have to take your plate, go back to the queue. So the second person will use the table to eat his food. So this is exactly how the concept is actually working. So everyone taking turn, something like a round robin kind of things. But if you can actually do this very, very fast, then you can support not only 4 users, you can support like maybe 40 users. Okay, if you are running a even higher clock speed, you can even support maybe 400 users. Okay, so this is exactly the advantage of TDM, where you can improve the performance by improving the clock speed of the multiplexer and the demultiplexer. Right, and then this is actually one of the, as I mentioned, this is actually one of the very popular technique, and then they are using time slot. Okay, each of these, this is a frame. This one is a frame. And each of the frame here, you got the multiple time slot. Then you have multiple time slot. For example, in this particular case here, each of the frame will have 3 time slots. So this is exactly what happened. So each of the user will have 1 time slot. And synchronous TDN, the word synchronous, syn. The word syn, this means synchronized. So synchronized means what? The multiplexer and the demultiplexer. So the two will have to be synchronized properly. So the two has to run at the same speed, running at the same clock speed. So in our daily life context, same thing here. So how do we synchronize? How do I synchronize with all of you? How do you know that this is our class? You know how our class has started. Where we all referring to the same clock, right? We all referring to the same clock. When I say 2 o'clock, your clock also showing 2 o'clock. So I said 2 o'clock we will start lectures. So you look at your watch, I look at my watch. See, when it is 2 o'clock, I will start. When it is 2 o'clock, you will come in. Right? So this is exactly what happened for synchronous system. So the multiplexer and the demultiplexer, they will have to synchronize under the same clock speed so that no one miss out. No one miss out. So if it is not synchronized, so you are late by half an hour, so you're going to miss, you see. So if your clock is not synchronized with my clock, your clock is half an hour late. So the moment when I already started my class, but you are still thinking that the class is not started, so you won't join the class, you see. So this is what we call not synchronized. So when the time is synchronized, when I say 2 o'clock, everyone see 2 o'clock, everyone will come in and we can start the lectures. So that's the whole concept. Huh? And then the problem with synchronous is actually you have sometimes you have empty space. Okay, this one is also empty. Okay, so you have empty space everywhere. So your transmission is not efficient. So how do you make it efficient under the time division multiplexing? So you just do some sort of data management. For example, you can do multi-level multiplexing. Okay, combine 2 to become 40. Okay, so you have how many users already? 1, 2, 3, 4, 5. It's about 5 users. Okay, instead of just 4 users only. So you can do this. These 2 users are the slow one. They only produce 20 kilobit per second. So it can be combined to become 40 kilobit per second. And then join with the others, multiplex with the others. And then another technique is called the multi-slot allocation. So this guy is actually quite fat. So it needs 50 kilobit per second, but the entire system running at 25 kilobit per second. Okay, so it can split 50 to 225. So it can even be multiplexed. So this is what we call the multi-slot. And then we can also do pulse stuffing, bit padding, or bit stuffing, depending on what is missing. Like for example, you compare this line, this is 50, the other one is 46. 46 and 50, there are some lacking. So you can actually patch another 4 kilobit into the into this 46. Then you will get 50. Okay, same as the others. So you can be multiplexed. Right. So these are actually the technique what we call the pulse stuffing, bit padding, and bit stuffing. Okay, and for synchronous TDM, of course, you need to do frame synchronization. As I said, everyone must be referring to the same clock. So how do they synchronize? They use frame synchronization. For example, the synchronized pattern is 101. So the first one is frame number 1 is 1, frame number 0 is 0, frame number 3 is 1. So it's 101. So it's actually following. Right? This is how time time synchronization can actually happen. Okay, I think these are same one. And then statistical time division multiplexing is another technique. Okay, it's another technique. Try to make full use of the line. If you look at this diagram here, you see the data is not consistent. You know, some users send more data, some users send less data. So it will actually making the multiplexing process not efficient. So how to make it efficient? Okay, how to make it efficient? So it's actually, so those are the empty space, like you can see, those are the empty space. So you fill the empty space with something else. So that everything is full. Everything is full. So statistical, based on statistic, to actually fill in those empty slots. And this one is basically telling us the differences between statistical and synchronous TDM. So basically they have 4 differences in terms of the addresses. So if you want to use statistical, so each of the time slot will need to carry the address information because they are not synchronized. So if you don't carry those address information, so a lot of time the demultiplexer will actually confuse. And of course, the slot size will also be affected as well, where time slot needs to be sufficiently large in order to efficiently deal with the needs to carry address information. So slot size needs to be made bigger to carry not only the data but also the address information. And they won't be under statistical. There won't be there's no synchronization bit because it is not synchronized. And of course, bandwidth is actually less. Why? You need to carry the overhead, the address information. You need to carry. That's why your bandwidth that you can offer for each channel is actually less. Right. So these are actually some of the implementation of this sort of statistical TDM system. For example, the T1 carrier, E1 carrier, Sonic, SDH, ISDN. So those are actually the network technology that is being adopting time division multiplexing so much. All right. And then limitation. Some of these FDM technique and TDM technique are actually very good on cable. But when they are actually being transmitted over the wireless medium, then they will have a lot of limitations. So these are some of the limitations that we can see. It said, this FDMA is limited by the bandwidth each user can get. Only a small fraction can be used by one of the user. And TDM will require a strict synchronization because you run on the same clock. That's why this is why you can send them, at a very high speed. In fact, the highest speed, the highest performance multiplexing is actually, if you talk about cable, it's actually TDM. TDM is actually one of the very, very efficient one. And of course, on the wireless medium, you don't use, the TDM is not so popular. People use CDM. Okay? CDM is called code division multiplexing. So what is code division multiplexing? In simple terms, it's just like everyone speak using their own code. So if you don't know the code, you cannot speak to that person. And because your code is different. So they all go by the code. So every network is being assigned a code. So you can multiple networks are all coexist at the same location and they can still communicate without any problem thanks to this code division multiplexing. Right? So they actually, each of network is being assigned a code. So just now I will say that they split the frequency, right? Then they split the time. And now CDM is actually they give different code to different user so that they can actually transmit it over the wireless medium. And the recipient can still easily retrieve the information by home in into that particular signal and then can use their own code to actually decrypt the transmission. So this is basically what happened to a wireless communication system, wireless communication networks. So this code division multiplexing technique can be further drilled down to like spread spectrum. So spread spectrum is one type of code division multiplexing. It is one type. And this spread spectrum is actually spreading the signal into very low frequency. So you can look at two different types of spread spectrum here. We have frequency hopping and direct sequence spread spectrum. So let's look at this is direct sequence. This is direct sequence spread spectrum. So initially you have a bandwidth of your signal, but after you've gone through the spreading process, you can see that your bandwidth has increased so much, becoming a new bandwidth. It will actually, that signal consume more bandwidth here. And the spreading process involve the spreading code. Okay, that's why it says each of the network will have their own spreading code. Okay, to actually spread the signal. This is something like encryption. If you want to see this one, like encryption. So you use a different code to encrypt, so that in between no one can actually read, can actually see your data, and this is how you can send the data safely to the destination. And then your recipient will be able to use the same spreading code to demultiplex it, to demultiplex, okay, to recover the signal back to its original form. This means from here to here, and then from here to here. Okay, so that you want to recover. This is your original. This is your original signal. Okay, and then frequency hopping, as you can understand, just now direct sequence spread spectrum, you spread the signal to make it better, to make it wider. And at the same time, when you actually do that, in fact, your signal is like this. Normally your signal is like this. So after you spread them, they will become shorter, but longer. So you can see the amplitude of the signal. Okay, the direct sequence one will have lower, and of course it will have a larger bandwidth as compared to the original one, which is less. Basically, you just press down the signal lah, so it will just be flattened. It is going to turn into something like this. Okay, so this is actually the basic concept. And as for frequency hopping, it is like hopping around. Okay? As you all know that the frequency is hopping around. So you don't use the same frequency to actually transmit all the time. So you're actually hopping around the frequency. For example, you look at this hopping sequence here that I'm drawing. Okay, the hopping sequence is 700, then 900, 300, 200, 400, 800, 500, 600. So this is one sequence. Okay, there was first started transmission at 700 kilohertz. After that, they changed to 900. So this one is only valid. This transmission for each of these frequency is only for a very short time only. So after that, what? After that, you will have repeat the sequence again: 700, 900, 300, 200, and blah blah blah. So this is another sequence, which is actually the same one, but it's keep repeating. So by jumping around using different frequency all at the same time, so what are the advantage? Advantage is that your frequency cannot be easily jammed because you are running at different frequency. For example, if you look at this one, this is frequency. The first one is 700. Second one is 900. The third one is 300. Fourth one is 200. And then fifth one is 400. Okay? You can see it as it changes. And the advantage of frequency hopping is that when you have an interference here, this interference is only affecting this frequency. So it will not kill your entire transmissions. Because your frequency is hopping around. You can see all the green dots here, your frequencies are hopping around. So only one being affected only over here. Okay, only one being affected. Not everyone. So that kind of interference is still bearable, still bearable by a lot of wireless transmission, especially in a very noisy factory. So this frequency hopping spectrum is extremely useful. The only problem with frequency hopping spectrum is that it has very small amount of bandwidth. If you compare, each of these is only this much of bandwidth only. So that's why they are very small. Instead of you can have everything. Okay? Under TDM, you will have everything all for yourself within that period of time. But this is frequency hopping, so they only occupied the network for a very small amount of time. So that's why performance-wise, frequency hopping spectrum, they have lousier performance as compared to direct sequence spectrum. Okay. So how does the signal being generated? First one is original signal going to a modulator. So this chip generator will actually generating the Baker code and then modulate it with this original signal, then they'll send out. So the signal is going to be something like this. Okay, the original one may be something like this. Okay, so this is exactly what happened. So this one is actually considered encoded with another code. So it's being protected. All right, so if you look at this one, the direct sequence spectrum. All these direct sequence spectrum and the frequency hopping spectrum, they all fall under the category of chord division multiplexing. So each of these techniques will have their unit set up for the transmitter and the receiver. You can see that this is the part where this red color dotted part is actually where the modulation is actually starting. But once everything done, transmit over the channel, receive. So they're going to undo the process to actually recover the original data. And this is another example that you can see. I think that's why I say by looking at more examples, then you will know how things are being mathematically combined, okay, and then extracted. So this is exactly what happened. Okay, I think in short, I would say that a lot of wireless system, a lot of wireless network, they have to use spread spectrum, which is a CDMA technique, called division multiplexing technique, to actually ensure that they are not easily jammed. They can survive in a very noisy environment. And then for the DSSS here, it can actually transmit at very low power mode. And then this one is usually used in military. If you do you watch movies, sometimes in the movie you will see that, this team of army going in, each of them using wireless to communicate with each other, to perform the planning. But halfway, their communication channel get jammed. They cannot talk to each other, there's no response. Why? It is because their transmission signal can be detected by the enemy, so the enemy will introduce jamming signal. So the moment we introduce jamming signal, so all your wireless, if the frequency is correct, then all your wireless communication will be disturbed. The worst case scenario is that you cannot communicate at all. Okay, so that's why the people introduce this kind of chord division multiplexing technique, such as the direct sequence spread spectrum. They can operate at very low signal power. What do I mean by low signal power? Let me draw the diagram. Initially, you will have signal like this, okay? But after you spread them, see, this one is very tall, easy to detect. If you look at this one is shorter, so it's harder to detect. Sometimes your enemy might treat them as a noise, as a background noise, which is not important. But in fact, you already communicate using this kind of signal, which your enemy cannot detect you. So this was the technique used in the military for like maybe 40 or 50 years ago. So people use this technique in military, but now this technique is made available, easily available to the entire community. So you can free of use of this concept. So people use this to build your wireless LAN, your Wi-Fi, where your Wi-Fi is based on this. And it's very rare you will find frequency hopping spread spectrum, but they are still exist. It's just that they are not that popular. So to find a frequency hopping type of product, you might have a lot of difficulties. Because the product is not easily available. All the Wi-Fi products, all the wireless networks products that is being sold in the market, mostly, I would say 99%, is actually based on direct sequence spectrum. Because which one has higher performance? Of course, the direct sequence one will have higher performance as compared to the frequency hopping. The frequency hopping just hopping, right, for a very small portion. And this is only for a very small portion of bandwidth on it. That's why even though they can survive all the noise, but the performance they can never be as good as the direct sequence. The direct sequence ones can use the entire channel. This one is only a small part. Then you jump around again. Right? So this is actually the two main concept that we're trying to introduce. You must remember all this happen. All these things happen at the physical layer. We are still at the physical layer and the network link layer. So these two layers will have the most complicated set of network technologies come into the pictures. Right? But the moment when you go to layer number 3, number 4, there is a very much protocol, very much standard. Not much option. For example, at the network layer, you choose IP, TCP IP. The moment when you choose TCP IP, at layer 3, you must run IP packets. At layer 4, you must either run TCP or UDP. So it's pretty straightforward in that particular case here. But for our case here, if you talk about layer 1 and layer 2, there are so many options. There's so many options that you can choose from. Because there are so many options. That's why it's actually full of possibility, right? Okay, so I hope these two actually clear your understanding. Because I'm not going to repeat everything. I just helped you to conclude and help you to highlight some of the very critical part of this learning unit. All right. Any questions that you would like to ask? Again, this is just a quick summary of what you have watched through the lecture video, and I'll just further summarize it again for you, okay, to actually make it easier for you to understand. Remember, multiplexing technique, they are different type, and they use in different type of application, different type of scenario. And the higher performance one, of course, it's actually the TDM and the wavelength division multiplexing, because each of the wavelength can actually carry a lot of data. Why? Because light source is running at very high frequency. It's in terahertz, meaning to say that the light source will have plenty of bandwidth. They will have so much of bandwidth that that can offer something like a future-proof type of applications. All right. Anything you want to ask? Are you still with me? Okay. A lot of you said no question. All right. So I will have some announcement to make to remind you that in less than 2 weeks time we're going to have, essentially 2 weeks time. In 2 weeks time we're going to have a mixed semester exam. So this mixed semester exam is all multiple choice, and it's for on the so we will have it on, if you check our elite page, then you will see that it's on the 13th of May. It's a Black Friday, actually. So I wish you luck. From 8 p.m. to 9 p.m. This is not open up the whole day. This is only open up for 1 hour, from 8 p.m. to 9 p.m. Okay, over Ellipse. So during that time, on the 13th of May, which is on a Friday evening, Friday night, Friday evening, 8 p.m. to 9 p.m., you have to log in to sit for the mid-semester exam. And it will consist of 50 multiple choice questions, multiple choice, 60 minutes, and it will cover 6 learning unit number 1 until learning unit number 6. So I think it is time for you to start preparing for this exam. One of the ways for you to prepare yourself is actually go through the I would say the tutorial questions, not the tutorial, quiz type of tutorial questions that you go through there to actually help you to understand. Right, so it's multiple choice, and everything is done online. I'm not sure if you have done any online before, but I believe you have online exam experience. And also remember, you cannot go back. You see, the moment, just like your quiz, you have 50 questions. Once you get on to the next question, then you cannot go back to the previous question, right? So this is one of the rules imposed for online exam, so that you cannot go back and change your answer once I don't know, someone share answer with you or whatever, so you cannot go back to change. So this is one of the techniques that is being used to minimize, not to say prevent, to minimize the number of cheating. Okay, the number of cheating during the exam. Let's see. So it's for some of you who haven't scanned your attendance, you can scan now. But I just would like to remind you about your mixed semester exam. It is for on the 13th of May. Just 1 hour only to answer 50 questions, and LU1 to LU6 until today, until what we have covered here today. So it's altogether 6 learning units. So make sure you go through that. A lot of this example inside your lecture slides are actually very useful as well. So I hope that you can actually make full use of those examples. Okay, any questions? I hope you are doing well, and you are going well with your assignment as well. Okay, because there will be a project coming out soon. So far, any questions? No? Everyone happy? Okay. Yep. Yeah. So just get ready for your exam, and then this is right after your semester break. Next week will be your semester break, so we won't have any lectures at all. So there is the time where you can make good use of your time to prepare for your mid-semester exam. All right. So any questions you can ask either in the group or anywhere okay, to actually ask for any questions. All right. So if you don't have any questions and you have already done scanning your QR code, then you may leave now. Thank you very much, and see you again next round.